Hello, am I audible? Can you hear me, Antho?
Yes, sir, I can.
Okay. So let's begin this session. Let me start by sharing my screen.
Okay, sir.
Hello and welcome to this TA session for week 5 for the course of Physics of Materials. This is an NPTEL course, and the instructor for this course is Professor Pratap Haridas from IITM. My name is Mohammad Tahseen. I'm the TA for this course, and I'm a PhD student at IISc. So let me start by giving you a brief overview of the things that we discussed last time. So last week we started our discussion on statistical mechanics, and prior to this statistical mechanics, we had discussed the Drude model for predicting the properties of thermal conductivity and electrical conductivity inside metallic solids. And then we commented that the Drude model actually works on the basis of the framework that makes Drude model work is that of the statistical mechanics and what's called the Maxwell-Boltzmann distribution. So that was the content for last week, and then we also discussed the limitations of and this Maxwell-Boltzmann statistics, and why we need to consider an alternative approach or an alternative statistics to account for some of the things that Drude model does not predict correctly. So let's briefly look at the things that we discussed. So we defined statistical mechanics as an approach in which we represent physical quantities in terms of their most probable states. Okay, and the most probable state, it is the state which gives us the equilibrium state of the system. This is the most likely state that the system can be found in. So we started with a simple example by considering a system of two particles, uh, and we impose a constraint on the system that the total energy of the system has to be 3 times epsilon, where here epsilon is some unit of energy, and we are imposing this constraint that the total energy should not exceed this 3 epsilon. Okay? And it should exactly be 3 epsilon, right? Not even lower than that. So the question then is, how can we arrange our two particles such that this constraint is obeyed? So we found that these are the only, if we list our all the energy levels that we have. So we have first which we can consider as the ground state, which is the zero energy, and then the first energy level, which is epsilon, and similarly 2 epsilon and 3 epsilon. And we then looked at what are all the configurations that can give rise to this system such that this constraint is obeyed. And we defined two terms, which was a macro state and a micro state. Okay. So a macro state refers to this information itself, right? There are two particles in a system, and the system has a total energy of 3 epsilon. This is the macro state. And the configurations, different configurations that can give rise to the system, these are called the micro states of that macro state. So in this case, where we just have two particles, these are the two configurations that can construct the system. So either we can have one particle in the zero energy state and one particle in the 3 epsilon energy state, or we could have one particle in 2 epsilon state and one particle in epsilon state energy level, right? So then we counted. So these are the two configurations that can give rise to this macro state. And here we make an important assumption that these particles are identical and distinguishable. Okay, and So distinct identical, it means they are identical in all the attributes that we can attribute to, all the properties that we can attribute to these two particles. Those attributes are the same for both particles. For example, we can consider the attributes like size or their mass or charge. So all such attributes are the same. So in that respect, these particles are identical, but they are also distinguishable, which means that I can tell one particle from the other, right? I always know that this particle here, no matter where it goes, I can follow it. And similarly for this particle. So what that means is that if we I can individually keep track of the particles, right? I can find their, in a way I can localize them at every moment of time. So so these are the definitions, and then we looked at what are the total number of configurations in which we can assemble this system by considering these particles as identical and distinguishable. So we found that the total ways in which we can arrange the system is 4, right? Because for this configuration there will be 2 microstates, and for this configuration there will be 2 microstates. Now this 2 comes from the consideration that these particles are distinguishable, right? If I take this particle and bring it here, and take this particle and bring it to this level, that will result in a different microstate, okay? Because these particles now have distinct identity, and that even in that case the total energy will be still be 3 epsilon. So the constraint on the system will be obeyed, and we will have 2 distinct microstates. And the same line of reasoning holds for this microstate as well. I can interchange these two, and I'll consider that as a different microstate because the particles are distinguishable, okay? So the total ways in which I can arrange this system is 4, 2 plus 2, right? So one thing that we can observe from this from these arrangements is that both the configurations here, right, both the microstates, they are equally probable. What I mean by that is, if I count the total number of configurations, that is 2 plus 2, 4, right? And out of those 4, 2 correspond to this one and 2 correspond to this one. So these arrangements, these are equally likely. And if you have such a system, there's an equal probability that you will find the system in this way or this way. So now let's take the same thing and take it to 3 particle system. And in this case we observed that here we have 3 different microstates, okay? And the constraint is still the same, that total energy should be equal to this 3 epsilon. And for this system I can find so these are the total all the possible configurations, and for each configuration I can find the number of ways in which I can build that configuration, okay? And so in the first case we observed that here there are 3 ways to basically arrange this system in this fashion, and for the second one there's only one way to arrange the system in this configuration, where all the particles are in one energy state. There's only one way to do it. Now we do not consider the permutations if, corresponding to the same energy level, right? It doesn't matter that if this particle, if I interchange these 2 particles, right, it will not count as a distinct microstate, right? Because these are identical and they occupy the same energy level. It's only if they shift the energy levels, then we can consider them as a different configuration. And and in this case, which is the third way to arrange this 3 particle system, we found that the total number of ways to arrange the system or to construct the system is 6, right? And we took the discussion to 4 particle system, and we found that there are again 3 different configurations. We can have a system in this configuration, or this configuration. And in a 4 particle system, what we found was corresponding to this microstate there are 4 ways. Corresponding to this microstate there are 12 ways, 12 possible ways of constructing this, 12 permutations basically. And corresponding to this system there are 4 configurations. So if we compare now our 2 particle system, 3 particle system and 4 particle system, what we observe is that uh, here we had 2 ways of arrangement and both were equally likely in 2 particle system. In the 3 particle system there were total 10 possible arrangements, and we see the most probable state had 6 ways in which that could be assembled, and the other 2 microstates had 3 ways and 1 way. Similarly, in the 4 particle system, 2 of the microstates had 4 ways of arrangement, right? And 1 microstate had 12 ways of 12 permutations, right? So what we see here is that as the number of particles increase, the most probable value or the most probable microstate has more number of permutations, right, than as compared to the other microstates. Because if you see the difference here in this case it's 0, the difference is 0. In this case the difference between the most probable state and the next most probable state it's 3, while in this case it's 8, right, 12 minus 4. So then we made the assumption, or we can even show this by induction, that as the number of particles in the system increase, this number, which is the most probable state, it not only it increases in value as compared to all the other values, but this number becomes greater than all the values combined, all other values combined, right? So for example, if I add here 4 plus 4, that will give me 8, and which is still less than this most probable state. And this difference only keeps on growing as the number of particles increase in the system. And this is the most probable state of the system, which has the most number of permutations corresponding to that energy level. So then we made some simple calculation for a system of n particles, and we came up. So we extend this concept now from 2 particle system, 3 particle system, 4 to a general system which has n particles, and we found this formula. Okay, we found that the total number of ways of arranging that system is capital N factorial divided by n naught factorial, n1 factorial, n2 factorial, and so on. Okay, and this capital N is the total number of particles present in the system, and these small n with indices 1, 2, and so on, these represent the number of particles in the in different energy levels. Okay, so for example here n0 or n naught in this case corresponds to the energy level epsilon naught, epsilon 1, epsilon 2, and so on, right? So this is now the total number of ways in which we can arrange a particular system, and I called this number, I represented this number by omega. Okay, and then we did some further calculation. Basically we want to maximize this omega, okay, or in other words we want to find a distribution of particles, of our classical particles. We want to find a distribution which leads to this omega being maximum. Okay, and with a little bit of calculation which I will not repeat, we found that this problem can be it can be converted into an optimization problem, where we want to have this kind of a situation that the derivatives of this natural log of omega with respect to number of particles in ith state, that should be 0, right? Because this is the condition for finding a maximum or minimum, right? The derivative should vanish, and this is our objective function now, and the constraints on the system are that the sum of so at that particular distribution which gives us the maximum omega, the total number of change of particles, if we consider the sum of changes of the particles, the number of particles in each state, that should come up to 0. So this was simple to understand. What we meant by here is, if we have some equilibrium distribution which maximizes the omega, and let's say in that configuration this is our epsilon n and this is epsilon n minus 1. So let's assume that this is the configuration which gives us the maximum value of omega. Now at that state, if I take one particle from here, so this has 3 particles and this has 2 particles, right? If I take this particle and bring it here, so there will be no particle here, right? But this particle will add up here. So this state has lost one particle, so we'll give it a value of -1, because that is the change in number of particles, and this state has gained one particle, right? So if we add these changes over all the possible states, that should evaluate to 0, right? As we can see in this case. Okay, and third constraint is that the energy changes corresponding to such the energy changes, oh sorry, I lost my screen. Yeah, so the energy changes corresponding to such jumps, that should also be 0. Okay, and if we solve this optimization problem, we get this expression for Ni. So what it does is, this expression relates relates Ni to epsilon I. Okay, Ni is the number of particles in ith state, ith energy level, and epsilon I, this is the number of, no, not the number, but the energy of ith state. So I am using these words energy state and energy levels interchangeably. So this is the energy of ith state and this is number of particles in that state, okay, in ith state. And we see that this distribution depends on the value of temperature, right? And there's a T here and the Boltzmann constant, which is constant, so it won't affect the distribution, but it is a function of temperature, right? And then this P here, it's this sum basically, and it's called a partition function. Okay, basically this will be a constant. It will not change over the as we change the distribution. Okay, so this is also a constant. So basically this number of states corresponding to an energy level, it has an exponential distribution. That is the crux of the Maxwell-Boltzmann distribution. Okay, so the distribution is exponential. Distribution is exponential. So that is the takeaway message from the this Maxwell-Boltzmann distribution, which considers the particles to be classical. So if we take a plot, so this is the exponential plot now, right? Here we are plotting the number of states. So actually it's not the number of states, it should be the particles, number of particles actually, okay, number of particles in ith state, right? So we see that this distribution is exponential, and we already said that this depends on temperature. So if for some temperature T1 which is less than T2, okay, if T1 is less than T2, then we observe this trend. Okay, so the T1 is this curve in this pink color, and T2 is the temperature shown in the red color. So what we observe here is that greater the energy levels, as we increase the temperature, the energy states which have more energy, the higher energy states, they get populated more and more. Okay, and the energy states, the low energy states, okay, which are closer to the ground state, the number of particles there decrease, right? So that is what this Maxwell-Boltzmann distribution gives us. It basically gives us this like this expression, which is del ni or del t, how the number of particles in a given state change as a function of temperature. This is the quantity that is given to us by this Maxwell-Boltzmann statistics. And the final comment we made was that this value is this is the basically the reason why Drude model fails to explain, or it gives some far off values for certain quantities like the electronic specific heat, or the what you call the mean free path. Okay, so yeah, so now the question is that, can we have a better alternative which can give us better magnitude for this quantity? Okay, some can we have some other form of statistics which can give a more accurate description of this quantity that aligns well with the experimentally observed values? So that is the motivation for today's session. Okay, so let me start a new file. So this is week 5. Let me write the name of the course first. This is physics of materials. I should write it. This is an NPTEL course 2025. Okay, and we are in week 5. So the main topic of this week is finding an alternative to the Maxwell-Boltzmann statistics. So that's the aim. Okay, and in particular what we are going to be doing in this session is basically an introduction to quantum mechanics. Okay, and we'll try to motivate what's the need for quantum mechanical principles to be introduced so as to have a better prediction for certain quantities. Okay, and let me let me give you the big picture first. What we are going to be doing is we are heading towards the discussion on a modified model which is called the Drude-Sommerfeld model. Right? So this is where we are heading towards. It basically modifies the Drude model, and it introduces the principles of quantum mechanics into these basically finding the statistics of physical quantities. Okay, so because in this discussion that we had till now in the preceding sessions, all the particles were assumed to be classical, and even the electrons that are present inside this, which form this electron gas cloud in a metallic conductor, they were assumed to be classical particles. And that is the limitation of this Drude model. That's why it's not able to predict some properties correctly. So, okay, where do we begin with this? Yeah. So, so the main assumption that we made made by the Maxwell-Boltzmann statistics. It's that the particles are identical and distinguishable. Right? So this was the main assumption that was made by Maxwell-Boltzmann statistics, and based on this assumption, the number of permutations corresponding to a particular microstate were evaluated. Now, what actually happens is that this assumption is violated, okay, or I should say it's not applicable. This assumption is not applicable to electrons, okay, and we'll try to understand why it's not applicable to electrons, and this description or this discussion requires us to go into the history of quantum mechanics and how it emerged and why it emerged. It's only by considering those principles that we will be able to understand why electrons cannot be treated as identical and distinguishable particles, and what actually is the case, that electrons are identical, for sure, identical but not distinguishable. Okay, this is where we are headed towards. Okay, we have to understand why this happens. So let's try to understand. Okay, so let's first try to understand what's the different length scales that are involved in the discussion revolving the atomic physics. Okay, so what are the different types of particles that we know of? Okay, so first is the electrons, or I would put them at last. Let me go in order. We have atoms, and inside atoms we have protons and neutrons, which are present inside the nucleus, and then we have electrons, which revolve this nucleus. Okay, and if we look at typical length scales, the atoms have a length scale of 10 to the minus 10 meter. Okay, and it's also called angstrom. Similarly, protons have roughly they have a size of, the length scale involved is 10 to the minus 15 meter. Okay, it is also called a Fermi level. And same for neutrons. Okay, neutrons are also of the same size, and electrons, it's estimated. So this symbol that I am making, it means approximately equal to, right? Because our experimental techniques are not at these length scales. They are not reliable enough to pinpoint a particular value. Okay, so electrons are of the order of 10 to the minus 18 meter. Right? So we see that there's a significant drop in size as we go from atoms to electrons, right? And the change is of the order of 8 orders of magnitude change, which means that it's 8,000 times smaller than that of an atom, and that's a very considerable number. And this is the reason actually that they don't behave in the same way as the atoms behave in an ideal gas, right? Our first assumption was that electrons behave as an ideal gas inside the metallic conductor. So these size effects are very important to note. Okay, and now what happens is, for example, let's consider that we have two particles. Okay, let's say we have two cricket balls. I'll call this B1 and B2. Let's say these are two cricket balls, and let's say these collide with each other. We set them on a trajectory so that they collide with each other, right? Something like this. And after this collision, let's say this particle is bounced off here and this particle is bounced off here. And let me make one of them shaded so that we can track them better. So this will be the trajectory of the shaded ball and that of the unshaded ball, right? And so this kind of a situation makes sense in our common observation of the world as well. If we take two balls and we collide them at the same velocity, at the same angle with respect to some reference here, we will the trajectories will be a mirror image of each other, right? Because if we ensure that the particles are identical, so we assume that this kind of a situation would happen, and this sits very well with our observation of the world. But what happens if these particles are now electrons? Okay, and I'll call this E1 and E2. Let's say this is first electron, and yeah, so this is actually not I can't label them as E1 and E2. I can just say that there are two electrons. Okay, this picture is actually wrong, but just to convey the point that if we set these two electrons on a trajectory where they are expected to collide with each other, it may very well happen that somewhere when they get near enough, they could just swap with each other. Okay, it's something that is not very intuitive. That would not happen in this case, but it happens here in this case, or it could there's a probability actually that it could happen. These could actually swap. So what we would end up in having is that we won't be able to say with certainty whether electron first is here or here, and we won't be able to say whether electron 2 is here or here. So basically we lose that distinguishing property between the two electrons. So if we start with two electrons, we will still end up with two electrons, but we will not be able to say which is which. Okay, and the reason for this is that it's very tough to localize an electron and calculate its trajectory. Okay, there is always a probability factor associated with the location of an electron. Okay, and as we will see, we'll build more on these concepts. That there is actually a wave function which describes the likelihood of this electron being present at this position. So we can never say with certainty that the particle is here. Okay, and even if we make a remarkable guess that it is here, we lose all information of where it's headed. Okay, the momentum, what we call the momentum, right? So this is the Heisenberg's uncertainty principle at work here. We lose track of the momentum. So if we are let's say we on the other hand, if we are directing them towards one another, so we know their trajectories well, in that case, or their momentas, we know their momenta well, in that case we lose track of their position. right? So there's an inherent limitation to the accuracy with which we can predict the motion of these particles. So that is the reason that on this side I can't say that this is the electron that started from here or this is the electron that started from here, right? So what happens is electrons behave as identical and indistinguishable particles. Indistinguishable particles, right? So this is the reason that caused an error while we were dealing with the root model. Okay, and actually what we can say to be a bit more technical is that electrons behave as quantum particles. Okay, and now we need to understand what is this quantum particle and where does it all start from. Okay, and to understand this further, we have to look at the history of how this picture of quantum came into being, and why or how it helped to resolve some of the concepts in physics. Okay, so this is around the beginning of 20th century. Okay, so around the beginning of 20th century there were certain unresolved problems in physics. Okay, unresolved problems of physics, and the most famous of which unresolved, okay, and the most famous of which was the black body radiation. And the second one was photoelectric effect. Right? And there were some more. Okay, there was, for example, what we call the modified Compton scattering. Right? Or let me put it at D. So at 3 I'll put the discrete absorption or emission spectrum spectra, I should say, of atoms. Right? And it was believed that so we'll look at some of them in slightly more detail, but what was believed that all these problems, they could be there lies an explanation for these problems by existing theories. Okay, and it was believed that some slight modifications to the existing theory would be able to explain all these effects. That was the general belief, but no one had come up with an explanation or a theory to basically explain these effects. So what were these effects basically? So let's take the first one. Let's look at the black body radiation. Okay. So let me start on a new page. what is black body radiation. Okay. So the concept of black body, it's a body which absorbs all of the incident radiation or all of the radiation incident on it. Okay, now what does that mean? It means that if there is some body, okay, so this is some general body. So what happens with, so first just before that, what I should say is that all the common things between these problems, okay, there's a one common feature, there's a single thread which runs across these problems, is that all of them are related to the way the radiation interacts with matter. Okay, for example, in black body radiation you have a material body and radiation, and there are some questions that were not answerable at that moment. And similarly for photoelectric effect, and for again for discrete absorption spectra of atoms, what you are doing is you are shining radiation on the on atoms, which is matter, and then based on how they behave and what kind of output you get from those atoms, what kind of radiations you measure from there were some unresolved questions here, and similarly for Compton scattering as well. So what is this black body radiation now? Now again the problem is again same. If we have any general body, how does it relate to, or how does it interact with radiation? Okay, that's the question. So just a moment, excuse me for a moment please, I'll just be back. Yes, so we were discussing the black body radiation, and we said that this black body radiation, or the problem with this black body radiation, it's related to how radiation interacts with a material body. Okay, and this radiation is electromagnetic radiation. So what happens is, if you have a body, any general body, if you shine radiation on it, a part of the radiation is reflected from the body. Okay, a part of it is absorbed by the body. Okay, and a part of it is transmitted by the body. Okay, So these are the three things that happen. Either the body absorbs some energy from the radiation, or it reflects some of it, and it can also transmit some of the energy, right? So the question is, so we are discussing black body, right? So what is a black body in this context? So a black body, it's a body, so it's a hypothetical body basically. Hypothetical body which absorbs all radiation, all the incident radiation, right? So there are actually we define some coefficients for any body. We can define a reflection coefficient, right? Let's call it some RE. We can define a transmission coefficient, and similarly we can define this absorption coefficient, right? AE. So for black body, this reflection and transmission, it is 0. Okay, reflection coefficient is also 0, transmission coefficient is 0, and all the energy that is incident on this body, it gets absorbed, right? And it will continue to absorb this energy as long as the temperature of this body is it's lower than that of the surroundings, right? That's a necessary condition, otherwise it will violate the second law of thermodynamics, right? So as long as this body is cooler than its surroundings, all the radiation that you shine onto it, that will be absorbed, fully absorbed. No component of it will be reflected or transmitted. And it turns out that there's actually I'm sorry, the light went out, but I guess we should be fine. So uh, what happens is, for a black body, this reflection and transmission coefficient is 0, and all of the energy is absorbed. And the inverse is also true. Okay, if a black body is kept at a temperature which is greater than its surroundings, right? So in that case, it emits radiation at all wavelengths. Okay, so its behavior is very symmetrical. If it's hotter than its surroundings, it will emit radiation at all wavelengths or frequencies, and if it's cooler than its surroundings, it will absorb the radiation of all frequencies. Okay, and there is actually a this was shown by Kirchhoff. Okay, and sometimes it's called Kirchhoff's black body. So he came up with a construction which takes us very close to this black body behavior. Okay, so he basically considered something like this. Okay, something like this. So this is a spherical body. I can't show the third dimension here, but it's a spherical body with an opening here. Okay, and on the inside you are lining it with graphite. Now why graphite? Because the graphite has the reflection coefficient and the absorption coefficients, these are very close, so it has a good reflection coefficient. Okay, and it has a good absorption coefficient, but its coefficient of transmission is almost 0. Okay, and what happens is there was a conical, so this is a conical blip or a bump. A conical bump was kept here so that all the radiation which comes into this body, it gets reflected across throughout the body, but then there are further reflections. Okay, for example, if this is incident here, it will get reflected here, and from here it will get reflected somewhere here, and then from here it will get again reflected here, and then again here. And so basically there's very little probability for this incident radiation to leave from the way it came in. Okay, it gets reflected and finally it gets fully absorbed. Okay, so this construction gets us very close to an ideal black body behavior. Okay, and similarly, when the tests were conducted for this body, so this body was first when this body was kept at a hotter temperature than its surroundings, then it started emitting radiation, right, across all wavelengths. So that data was actually recorded. Okay, and it was plotted as follows. So it was plotted as follows. If this is the wavelength on the horizontal axis, and we have something called a spectral radiance, okay, on the y-axis. So we observed a distribution like that. Okay, now what is the spectral radiance? So spectral radiance, so first we have to define intensity. Okay, and as all of you might know, intensity is nothing but power per unit area. Power per unit area. Then spectral radiance, it's defined as intensity per unit wavelength. Right, so it's units, so if the units of intensity are power per unit area, right, so units of power are watt, and for area it's meter square. So for spectral radiance it would be watt per meter cube. Okay, so it basically gives us intensity at a particular wavelength. Okay, so when we talk about intensity, we refer to all of this energy that is released by the this black body. Okay, or no, so actually the correct way to define intensity is energy, no, not energy, but power emitted per unit area of the black body. Okay, across all wavelengths. But spectral radiance is intensity per unit wavelength, so it gives you a particular value of, at a particular wavelength, what's the value of intensity per unit area, right, power per unit area. So that quantity is called spectral radiance. So this trend was observed for this black body. Okay, and what is interesting here is that, let me copy this. Okay, so this is what was observed. So let's say this behavior of the body is for a temperature T1. We write it on the inner side, T1. So if we increase the temperature of this black body to slightly higher temperature, the experimentally observed data was something like this. Okay, this is the temperature T2, and T2 is greater than T1. Okay, and it was observed that as we increase the temperature of this black body, this peak value is shifted towards the left, and towards the left I mean towards a region of lower wavelength or higher frequency, right? Because frequency and wavelength are inversely related. So this is the region where the wavelength is less but the frequency is high, and similarly this is the region where frequency is high but where the frequency is less but wavelength is high. Okay, so at higher frequencies, so this peak is shifted towards the region of higher frequencies. So this is the experimental observation. Now what so again, like people began to wonder what happens inside the material that gives rise to this kind of behavior, and especially the people try to model this behavior by their knowledge of Maxwell-Boltzmann distribution. So they came up with, so the two important names in this context are Rayleigh and Jeans, and they gave a law which is called a Rayleigh-Jeans law, and this law is based on Maxwell-Boltzmann statistics that we discussed. Okay, so the derivations are a little bit elaborate, so I'll not go into the exact derivations, but what they showed was the value of this spectral radiance, let's call it by, we will denote it by E, right? So E is a function of lambda, which is the wavelength, as well as the temperature, right? That's what we can see from the graph. The spectral radiance changes with temperature as well as wavelength, and they found that the expression was 8 pi kb T over lambda to the 4. Okay, so this is the expression that they came up with. So but there is a flaw in this expression, that if we observe that as lambda goes to 0, right, as lambda moves closer to 0, the value of this expression should blow up, right? It will get incredibly large for smaller values of lambda, because there's a power 4 factor associated here. So if we try to plot this and the experimental data together so as to compare, okay, and this is again spectral radiance E, and we are plotting it against lambda, and let's say that at a particular T the observed experimental data is something like this. Okay, and then what this Rayleigh-Jeans law predicts is a distribution like this. Not able to draw a curve. So, okay, I'll try to be okay, something like this, right? This should be the distribution corresponding to the Rayleigh-Jeans law. So as lambda gets smaller and smaller, basically this value should go higher and higher and higher. So it does not explain the black body behavior well. Okay, and it also comes from so basically this model again treats electrons as classical particles. just like our, let's say, cricket balls. Okay, and it's not able to explain this behavior correctly. So again, at that point, that people imagine that there could be small modification factor that could be basically accounted in to explain this behavior. That was a general belief. But what turned out to be the fact was, uh, Max Planck got interested in this problem. Okay, and he basically made an attempt to understand this behavior. Okay, so what he assumed, and this was an arbitrary assumption. Okay, arbitrary assumption. Like there is no well-defined reasoning behind this assumption that he made, but there's a little intuition as to what could have made him make this assumption. So the assumption is that um so this assumption has certain many levels. Okay, first level is that uh, at a particular frequency, okay, so when we define frequency, we also know its wavelength because they are inversely proportional. Okay, so at a particular frequency or wavelength, an oscillator, and I will put it in brackets, gets activated in the system which emits energy that is proportional to this frequency. Okay, so what he basically said, that energy is proportional to nu, and nu is the frequency. Okay, so this assumption comes from the fact that if we look at the region of high frequency, we see that there's very little energy corresponding to that frequencies, right? So what he assumed was that at higher frequencies, you basically your if so yeah so let's basically backtrack a little and see what are the assumptions of this, not the assumption but the consequence of this Rayleigh-Jean's law. Okay, so Rayleigh-Jean's law says that as you get closer and closer to this higher frequency region, the energy of the system should go on rising and rising, right? So it basically says that the body should have an infinite amount of energy, right? So that is the classical picture. So classical mechanics tells us that the system should have an infinite amount of energy, but that's not the case. It violates physical constraints as well as our common observations. So what actually happens is that this phenomena was actually called the ultraviolet catastrophe. Okay, here in this region where it predicts an infinite amount of energy, this is called an ultraviolet catastrophe. Okay, and this is the failure of Rayleigh-Jean's law, right? So what Max Planck assumed was that inside this frequency, because the body has a limited energy, it does not have an infinite amount of energy. So the energy which has the highest frequency, okay, that content of energy is low. Okay, that's basically what he assumed here, by saying that at a particular frequency there's an oscillator inside the system. So an oscillator can be kind of, let's say, electron jumping states from one state to another. So only that frequency will get activated. uh, um, let me say it clearly. Yeah. So what he said was that the energy of that oscillator which gets activated at a particular frequency, the energy of that particle or that oscillator is directly proportional to the frequency. So basically what he said was that if an oscillator gets activated in this regime, that oscillator will have very high energy. Okay. And if an oscillator gets activated here, that will have very low energy. Okay. So let's write it. Okay. So oscillators here have high, sorry, no, this will have low energy because frequency is less here, the wavelength is high, frequency is less, so the energy of oscillators which get activated in this region, they contribute to a lower energy. And here in this region, the oscillators which get activated have high energy. Okay. But it still doesn't explain why the curve drops down here, right? And why the so basically, yeah, it doesn't explain this portion of the curve, this assumption, as of yet. So but this assumption that he made, it had a let's see how it basically modifies the calculations. So when he made this assumption, he just assumed a constant to make this into an equation, make this proportionality into an equation. He called it h. Okay. And this h later came to be known as Planck's constant. So this is what's called the Planck's equation, right? So it equates the energy of a particular oscillator to the frequency at which that oscillator gets activated. And it further says that if the frequency is less than this nu, this oscillator which emits an energy E, it will never get activated. Okay, no matter what the intensity of the radiation is, if the frequency of radiation is less than nu, an oscillator which emits an energy of h nu will never get activated, right? So this is the main assumption which changed everything, because the classical particles, right, are activated. And when I say are activated, this means that they interact with a radiation of arbitrary frequency, right? So for example, if we have a cricket ball here, and let's say that there is let's say this cricket ball is charged. Okay, let's say there's a positive charge here on this cricket ball, and let's say I put it in a field. Okay, let's say that this is my electric field, right? So what it says is, so what do we expect? We expect that no matter how strong this electric field is, so there is an electric field here, right? So it says that no matter how strong this electric field or how weak this electric field is, this charged particle will always interact with this electric field, right? So let me write electric field, because I am already using E for energy, right? This is what we assume or what we expect from a classical particle. But what Max Planck said, that if same is the reason, if you have a similar situation where you have a quantum particle, okay, and we call it an oscillator, let's say this is some kind of a quantum oscillator, and there's a radiation incident on this which has an energy. Let's say this oscillator, the natural frequency for this oscillator is, or the energy at which this particular oscillator can emit energy is some E naught. Okay, and what it says is that radiation if this radiation is of an energy less than E naught, then this radiation will not be able to excite this particle. Okay, and the minimum energy that is needed to excite this oscillator, that would be E naught will be equal to H nu naught. Okay, and this nu naught is the minimum frequency needed to excite this oscillator. Okay, so when he made this assumption, okay, and he basically said that this this exchange of energy, it does not happen in a continuous manner, right? It happens through this discrete step of energy. This is the minimum energy needed to excite this quantum oscillator, which has an energy E naught, as compared to a classical case. If this is a classical oscillator and this radiation is incident on it, no matter what the frequency of this radiation is, it will always excite this oscillator. But if it's a quantum oscillator, then it will not be able to excite this oscillator. This radiation will not be able to excite this oscillator unless it has a frequency of this nu naught, which is given by E naught by H. Okay, so this is the main difference. And once he made this assumption, this expression that he got, modified expression, okay, what's called the Planck's law. So modified expression came out to be something like E of nu comma t is equal to, or let me call it lambda only. I'll write the expression in terms of wavelength. So this was a modified expression. Okay, and if we take the assumption that for large lambda, we see that, let me call it E modified. Okay, E modified. Okay, now for large lambda, what happens is this E modified, it becomes approximately equal to E lambda t. So for a region of large wavelength, which is this region, okay, it correctly it coincides with the Rayleigh-Jeans law. So this part of the curve, it can account for this part of the curve very well, right? Now at this part, in this part of the curve where the frequency is high, okay, and the lambda is low, we see that it does not blow up. The expression does not blow up. Okay, it gives us a finite value even in this region. Then what Planck did was he adjusted. So there is one unknown parameter here, which is H, right? The unknown parameter here is H. So what Planck did was he assumed different values of this H to make his curve fit the experimental curve. Okay, and when he assumed the value of H to be, by trial and error, 6.55 into 10 to the power 34 joule second, he saw that his curve fitted the experimental curve exactly for both high frequency as well as low frequency limits. Okay, So this is how he found the value for this h, which is now known as a Planck's constant. Okay, and currently the present accepted value for this is 6.26 into 10 to the power minus 34 joule second, right? So this is the currently accepted value. So the whole game changed by this assumption that the energy does not continuously interact with matter, but it does so only in discrete energy steps, and this energy step later came to be known as one quantum of energy. Okay, this is called one quantum of energy. So that is the contribution of Max Planck to this whole, and it basically started the foundation of quantum mechanics. This was the first theoretical model which was able to explain the black body radiation. Okay. So after this, there was another effect which was called the photoelectric effect. Okay, photoelectric effect. And what is photoelectric effect? The photoelectric effect is, it's an experiment, okay, where you have some material, okay, and this is highly polished surface of some material. Okay, let me call it polished surface. And let's assume that this polished surface is that of a metal. Okay, and what this photoelectric effect says, that if you shine light onto this, okay, light or radiation in general on this metal, it knocks out electrons from this. So this effect was known much before Max Planck introduced his theory. Okay, this experiment was done much before that, and it was known that once you shine this surface with some radiation, electrons are ejected. And there were further few things that were known about these electrons. The first of which was so no electrons are ejected unless the frequency of the radiation crosses a particular value. Okay, these are all the experimental observations that were known to people. Okay, so unless that, so if we start with a very low value of frequency, we will not see any electrons here, and as we keep increasing the radiation, this frequency of this radiation, at some particular value we see that the electrons are emitted. Okay, the second observation that was known was that the kinetic energy, so once the electrons are emitted, the kinetic energy of those electrons increases as the frequency increases. Okay, and third observation that was known to people was that even if the intensity, okay, so one observation that was known as the number of particles or number of electrons ejected, like the strength of this electron beam, the number of electrons ejected is not dependent on frequency, right? This is very crucial. So on one hand we see that whether electrons will emit or not, that depends on frequency, right? Unless you cross a particular value of frequency, the electrons will not be ejected. On the other hand, the number of electrons that are ejected, that does not depend on frequency. Okay, it only depends on intensity. Okay, so it depends only on intensity, right? So these are some of the observations that were known, but again there was no theory which could explain this. There was no theory which was built on classical principles that could understand and that could explain this behavior, unless Einstein came into the picture, and he used this idea of Max Planck to come up with an equation that the kinetic energy of ejected electron, okay, this is the kinetic energy of ejected electron, it is equal to h nu minus phi, right? This is the famous equation which got him the Nobel Prize. Okay, and here he used the idea that this h nu, it again comes from Planck's assumptions, Max Planck's assumptions, but in a different, there's one difference that I will highlight. Okay, so what Einstein said that this incident the incident radiation, if it has energy equal to h nu, the photons of this radiation, if they have energy equal to h nu, then the kinetic energy of ejected electron, right, that will be given by basically h nu minus phi, and this phi is known as the work function of the material. So there's a particular threshold value. For example, if we equate, so when will this velocity be zero? Okay, when the electron is just about to emit from the surface, at that value of frequency, we can say that this energy is zero, right? The kinetic energy is zero. When we increase frequency gradually, at some critical value of frequency, the electron will have the tendency to leave the surface of the metal, and at that value of frequency, the kinetic energy will be zero. So the entire energy of the radiation will go into knocking off the electron from its atom, right? And that entire energy will get converted into just removing it from the atom. So no energy will go into contributing towards the kinetic energy of electron. So at that time, this kinetic energy is zero, and we get that h nu equals phi. So this gives us the work function of that material, right? So the first frequency at which we start to observe, or let me call it now nu naught, okay, the first frequency at which we start seeing the emission of the electron, that helps us to calculate this phi, which is the work function. Now the difference between this photoelectric effect and Max Planck's effect was, here Einstein he basically hypothesized or proposed that the incident radiation itself is quantized. Okay, the energy of the radiation is quantized, right? So this is incident radiation. But what did Max Planck say in his theory, right? He assumed that the material has some kind of quantum oscillators inside it, right? So this is the difference here. Planck assumed that the behavior of material itself, that was behaving like a quantum oscillator. Okay, and he did not basically comment on the radiation here. He assumed the radiation to be a continuum of energy, which is available at all frequencies and all wavelength stars, and he assumed that the material itself would get excited if the available energy is of this order, right? But what Einstein proposed, or in his theory, he basically imagined this radiation itself to be composed of quantized particles, like photons. So that was the main difference between Max Planck's theory and Einstein's theory. So Einstein basically used the idea of Max Planck to come up with this equation, right? So in a way, he extended this concept of quantization of energy from material to the radiation itself. Okay, so that so this was one another phenomena that was successfully explained by the quantum by considering radiation as quantum particles. Okay, so this is how the subject of quantum mechanics developed and how it was able to explain the theories or the questions that were left unanswered. So another important milestone was that of uh, Louis de Broglie, okay, or Louis de Broglie as uh, the French call him. Okay, so what he proposed was that for any particle, okay, so basically he contributed towards the wave particle duality, right? So what was the need for this? Because so till Max Planck's experiments, it was assumed that this light or the radiation was a wave, okay, which had certain energy associated with it. But now Einstein had showed that we could treat this radiation as composed of photons of particular energy. So now the question again, that the question that emerged is radiation, is it a particle or is it a wave? Okay, and that made this Louis de Broglie to come up with his equation, in which he said, so he wrote this statement, and it is not just applicable to photons or radiation. He said that it applies to all materials, applies to all matter, right? No matter whether you're talking about atoms or particles or radiation, everything has this nature. Every matter in this universe, it has a dual nature. Okay, it has a certain wavelength associated with it, and it has a certain momentum associated with it, and these are related by the factor h, which is the Planck's constant. Okay, so he basically unified all of this both these behaviors into a single equation. And yeah, so again, if we see that for large momentum, okay, if momentum is large, lambda is very less, and vice versa, right? If lambda is less, no, sorry, if lambda is large, then p is less, right? So for, and what is p? P is momentum, right? It's mass times velocity. Okay, so if we consider two particles which are moving at same velocity, right? So the particle which has a greater mass will have lesser wavelength, okay, lesser magnitude of wavelength, and this wavelength is actually called de Broglie's wavelength. Okay, de Broglie's wavelength. So basically, this is the situation that is applicable to our common experiences, right? We have objects whose mass is 10 power 18 times greater than that of electron. So we see that for those particles, their wave nature is extremely their wave nature is not that amplified. Okay, but if we talk about subatomic particles, whose mass is very low, for them lambda is large. Did I make a mistake here? No, I think yeah, we are fine. Okay, so we see, right? So this unifies the wave and particle nature of all matter. Okay, so we see that if we are dealing with subatomic particles, their wave-like nature becomes more prominent as compared to our classical particles, or particles that we see at micro and nano levels. Their behavior is more like classical particles, right? So this was an important another important result in this development of quantum mechanics. And one more which is kind of important, okay, and that was the atomic spectra. So atomic spectra is discrete, okay, and this was one more puzzle that was not solved in the beginning of 20th century. And what this basically means, that if you have some kind of a rarefied gas, okay, a gas whose pressure has been reduced so that it can freely flow around in some chamber, okay, and you basically connect it to a battery, okay. So this is evacuated chamber, right? So there is a rarefied gas present inside this chamber, and you are applying some voltage here and here. Right? So what happens is the electrons get emitted from let's say this end of the conductor to this end. Okay, there are two conductors or electrodes present here and here, charged plates, what we call them. And so these electrons, they move around and try to get to this positive plate, okay. And what happens is, as they travel across this gas, they basically knock off electrons from, or they excite the electrons of these atoms that are present here. Let's say these are atoms, and the atoms have, let's say, different shells, right? There's a nucleus, and then electrons are revolving around the nucleus in different orbits, right? Something like this. And let's say that there's one particle which is present here, and when this electron that is knocked off from this plate, when that interacts with this electron, it gets excited and it goes into an excited state, okay. It goes into another orbit, and when that excited electron, when that comes back to its original state, okay, on the original energy level, it radiates energy, okay. It radiates energy on de-excitation, and what happens is that this energy, this radiation, has a particular wavelength, okay, and this is called the spectrum. In this case, it will be called the emission spectrum, okay, because so there are basically two types of spectra. One, there is an emission spectrum and there is an absorption spectrum, and in this case, since this is emitted by the electron, this will be called a basically an emission spectrum, okay. And what was known was that this emission spectrum emission spectrum is discrete. So what does that mean? Emission spectrum is discrete. It means that if you look at the wavelengths that are emitted from this atom, okay, those wavelengths, let's see, these are wavelengths. Emitted, okay. So these wavelengths are, let's say this wavelength is emitted, then in this neighborhood there will not be any other wavelength which will be emitted, and some other wavelength is emitted, let's say here, this wavelength is emitted, and let's say this wavelength is emitted, okay. And these things happen, these different wavelengths are emitted as you change the voltage here, okay. So they can be observed as you change this voltage here. So if you slightly turn your voltage up, so let's say at some voltage this wavelength is emitted, okay. Now what you would expect is, if you increase this V slowly by a little bit, you would assume that maybe this wavelength or this wavelength will be emitted, right? Because if you change V by a little bit, you expect that this will also shift either here or here, but that does not happen, okay. Unless you change this V by a certain amount, then you observe some other line here, okay, some other wavelength is emitted. Or similarly, if you, let's say, decrease it, you could observe some other wavelength being emitted, okay. So this is called discreteness, okay. It's not a continuous spectrum. There are huge gaps, identifiable gaps, which helps you distinguish these different wavelengths. And this phenomena, it was not very well understood, what causes this discrete spectrum, okay. And here Niels Bohr made an important contribution. So he basically did his calculations all for hydrogen atoms. And he could explain through his theory. He could explain this discrete emission spectrum for hydrogen atom. Okay. So what basically Niels Bohr assumed was that if this is, let's say, an atom, and this is the nucleus, okay, so let's say this is the positive charge of the nucleus due to the proton, and there will be some electron here, okay. So first of all, before even Niels Bohr began his work, there were questions regarding the structure of atom, right? Questions regarding the structure. Okay. So at this time, at Niels Bohr's time, what was the progress of scientific world was that atoms had been discovered, okay, by Rutherford's experiment. Electrons were discovered by J.J. Thomson. Similarly, protons were discovered, I guess, by Chadwick, or it was for neutrons. So basically, we knew all the subatomic particles what were present inside the atom, but we did not know the structure of atom. How are these all basically positioned and structured inside the atom? Okay. We had some ideas. For example, I guess it was Rutherford's experiment, where he said that when he shined radiation, I think alpha rays, onto the gold specimen, he observed with that lot of them were recovered undeflected. He had basically a screen here, and he could see large number of them were undeflected. In the center there was some zone where he could observe that the scattering was very large, right? So there were some preliminary things known about how an atom could look like, but the stability of atom, right, what makes an atom stable, that was not known, right? So why would this configuration be stable? For example, there's a positive charge here, there's a negative charge here, right? It could just attract this, right? It's very easy to assume or reasonable to say that this will get attracted and the whole atom will collapse to a nucleus, right? So what gives stability to this atom? That was one question. So there was even one electromagnetic theory which attempted to solve this puzzle by saying that the electrons revolve around this nucleus. Okay, uh, so there was that idea present before Bohr itself, that these electrons, they are not stationary but they keep revolving around this nucleus. But in that case, what would happen is that this electron, which has a certain energy, if it starts moving, we know that a moving electric field, because this is a charge, right? So a moving charge produces a magnetic field, right? So this would basically produce ripples in space of both electrical as well as magnetic fields, and it will continuously lose energy, right? And once it loses energy, it can again, it should spiral back and fall into the center of the nucleus. So even the classical electromagnetic theory as developed by Maxwell, that was not sufficient to understand the stability of this atom, right? So here Niels Bohr made an assumption, or basically he built a theory which not only explained the stability of atom here, but also he gave reasons that why do we see this discrete atomic spectra. Okay, so in his single theory he could explain both of these fundamental observations that were made by a lot of people. Okay, so mainly his postulates were that I will highlight the main postulate of his theory, which was that angular momentum of the electron is quantized. Okay, and how do we calculate angular momentum? Angular momentum is calculated as m times v cross r. Okay, actually it is r cross v, but yeah, it's either v cross, but I think most probably it's r cross v. So this is the angular momentum L, and he said that this angular momentum, it cannot take continuous values, it takes values such that those values will be equal to this. Okay, this was his main assumption. So again, this again borrows from Max Planck's ideas. Okay, so basically every quantity is now being thought of as being quantized, okay, instead of being continuous. Earlier it was thought, or it was pretty much known, that L could take any arbitrary values. There was no reason to believe that L could have quantized values, and this assumption was made by Niels Bohr, and he came up with his model of atom. So basically he built all his theory to explain hydrogen atom, and with time people were able to apply this to other atoms and explain the discrete atomic spectra of every other atom as well. Okay, but this was his main assumption, right? And he could calculate, theoretically he could calculate the radius of atom, right? Actually he could calculate the radius of nth energy level, nth, let's say nth orbit. Okay, if there's an electron present in the nth orbit, what would be the energy corresponding to that? So he could predict this. He could predict the radius of nth orbit. Okay, and since hydrogen atom has only one orbit, so he came out with this value, right? It's of the value of, oh no, I think it's 0.52, something like this. Okay, and the energy is minus 13.6 electron volts for a hydrogen atom, right? So in general he came up with the expressions for these quantities. Okay, for hydrogen atom they simplify to these values, and he could also predict the wavelengths of emission spectrum. Wavelengths of emission spectrum. He could even theoretically find an explanation and predict the values of all the emissions that are possible in hydrogen atom. Okay, so even he was awarded a Nobel Prize in 1922 for his model of atom, right? And Max Planck. So okay, so let's talk about all the Nobel Prizes that have been given in this field, right? So first one was Max Planck. He received Nobel Prize for explaining the black body behavior in, I guess, 1918. Okay, and then Einstein, although he did groundbreaking work on relativity, but he got Nobel Prize for his photoelectric theory, and it was in 1921. And then Niels Bohr got it in 1922. And I think De Broglie also got a Nobel Prize. I'm not sure about the year. Yeah, I found it. It's 1929. Okay, this was Louis De Broglie. He got in 1929 for his famous duality formula. And one final thing that I would like to say, and then we'll conclude this session on quantum mechanics, is that the famous, probably the most famous thing that comes to mind when one hears quantum mechanics, that is Schrodinger's equation, right? So what is this Schrodinger's equation? Okay, or what was the need for this Schrodinger to come up with this equation? Okay, so if we go back to De Broglie's equation, right? So he said that all matter behaves like a wave. That was his one-liner statement. All material particles behave like a wave, right? But the question was all the waves that were known at that time. Okay, what are the different types of waves we have? Okay, I'll come to the question later, but let's first ask the question, okay, if all matter is a wave, what are the different kinds of waves that are possible? Okay, so the waves that were known at that time were let's say acoustic waves, then there were elastic waves. These are pretty similar actually, acoustic and elastic waves. Acoustic waves are found in fluids, gases, and elastic waves are the ones that propagate in solids. Okay, and then they could have types like transverse waves or longitudinal waves and all that. And then there were electromagnetic waves, right? So these were the main types of waves that were known at the time. Okay, and the main difference between these types of waves were these waves on the left required a medium to exist and to propagate, and these were independent of a medium. They did not need any medium to propagate. Okay, but so this was the difference between the two, but the similarity was all waves obeyed a wave equation. Okay, and what is that wave equation? For example, let's say that there's an elastic string. Okay, let me make it like a string, right? This is a string fixed at one end, and let's say here you are exciting this string. Okay, you are just moving this up and down to create a wave in the string. Okay, so or in maybe a more simpler example is that of a spring mass system. Okay, if we excite this mass, let's say the spring constant here is k, and we excite this mass with a frequency of omega, which is, let's say that the force acting on this particle is a cos omega t or something, right? Then this also displays a wave behavior. Okay, and both of these waves actually obey the wave equation, which is that del square x by del square u by del x square is equal to 1 by c square del square u by del t square. Okay, so this is the wave equation, right, that is obeyed by these mechanical systems. And for electrical systems, I think you have here, so the electric field and the magnetic field, right, those are the components of the electromagnetic radiation. They individually define satisfy this wave equation, and the C in that case comes out to be 1 upon square root of mu naught epsilon naught, and this is what gives us the velocity of light, right, in that case. So here in this equation, this c refers to the speed of the wave. But the point here is that all known waves at that system, they came from some equation, they satisfied a wave equation. So the question that was posed to de Broglie was that if all particles define waves, what is the governing equation for that wave? Right? So this is the question that motivated Schrödinger to come up with his equation. Right? So what he said was, he basically formulated an equation. So I'll write the equation directly, although we can even argue that what the different terms are and where they come from. So we can basically write this wave equation from the consideration of conservation of energy itself. Okay, and this is the wave equation, Schrödinger's wave equation. Okay, so this is one of the forms in which it is written. There is actually, so this is a compact form, and sometimes physicists and mathematicians like to compact things up, but if we slightly elaborate it, we can also in a more readable way. The equation reads like, just a moment, yeah, so the equation can also be written as h cross, where h cross is nothing but the Planck's constant divided by 2 pi. Okay, so this can also be written as 2m del square psi upon del x square plus v of xt equals I, the imaginary number, h cross del psi over del t. Okay, this is the Schrödinger's equation written for one variable, okay, one spatial dimension. Here the only variable is x, the space variable is x and the time variable is t. Here in this equation we are using a gradient. Okay, this gradient basically means these partial derivatives are taken in every every direction. Okay, so that's a so that actually this equation can be considered as a set of three equations. This is a vector equation. Okay, so gradient square is nothing but del square by del x square I plus del square by del y square j plus del square by del z square k. Okay, so that's written for 3 dimensions and this one is written for 1 dimension. So what are the different terms in this equation? So here m, it's the mass of the particle for which we are writing this whole equation. Okay, x is the variation in space. For example, if a particle is given that it's moving in 1 dimension, then x represents the position at which the particle is. Psi, it's called a wave function. Okay, and so this is basically the variable which defines the wave. So if psi is known, then everything about the system is known. Okay, v is potential. So basically this potential captures all the effects of external forces that are applicable to the system, right? This, for example, this potential could be gravitational potential, it could be electrostatic potential or any other potential. Okay, and Schrodinger's equation, it is not just applicable to subatomic particles and electrons and protons in general. In particular, it is applicable to any matter and any kind of particle in general. Okay, because it's a fundamental equation. And here we have the derivative of psi, the wave function with respect to time. Okay, so this equation is I mean, it's still considered as something very non-intuitive, right? Something that people don't fully have a understanding of, even to this date. But this expression, or this Schrodinger's equation, it is able to explain most of the behaviors that are seen in the atomic situations, right, in materials, and different properties, be it electrical, thermal, optical, any kind of property, or even magnetic properties, they are very well defined within this quantum framework using the Schrodinger's equation. Okay, so this was a brief introduction to quantum mechanics and what was the different. So yeah, so the final point is that even Schrodinger got his Nobel Prize in 1933. Okay, 1933 he got the Nobel Prize. Right? So there are lot of Nobel Prizes have been given in this field, and it's the most recent thing that has happened in physics. Okay, from the beginning of 20th century, using these quantum mechanics ideas, the physics got a different turn. Okay, so what is our goal now? In probably the next TA session, we will use all these principles of quantum mechanics to arrive at Drude-Sommerfeld model, right? So this Sommerfeld model, and it will be based on Fermi-Dirac distributions or statistics, right, as compared to the classical theory, the Drude model and the Maxwell distributions, right? So in the classical case, we had Drude model which depended on Maxwell-Boltzmann statistics. In the Drude-Sommerfeld model, we will use the principle of quantum mechanics to make some corrections to the Drude model, and we will use an entirely different set of statistics, which is called the Fermi-Dirac statistics. And these statistics help us to understand or overcome the limitations of the basic Drude model that we discussed last time. Okay, so I'll stop here for this session. If there are any questions, then please ask. Okay, if anyone has any questions, please feel free to ask.
Sure, sir. Thank you.
Yeah, hi Lalita. Actually, you asked one question in the last TA session. It was about the formula for computing the number of permutations corresponding to a particular microstate. So that discussion will again, actually it will come up in the next TA session, and I will try to address that question in the next TA session. That discussion will be more relevant there. Okay.
Okay. Yes, sir.
Yeah. So someone is has written on chat that I have written blank. It's a oh yeah, yeah. Yeah, we should have a little respect for the names because these are big names. They have done a lot of work. So yeah, so the correct name is Max Planck, and I forgot to write a C before. Yeah, thank you Lalita for pointing that out. Okay. So thank you everyone for joining. I'll see you all next week.